All right, thank you, Nicholas. All right, so I'm here to talk about soiling and water management and how we can use simulation to improve the performance of a vehicle in relation to that. So I'm going to go through a little bit about motivation, and then I'm going to talk about simulation-driven design. Then I'll go through a few case studies and wrap up with a conclusion. So why should we care about soiling and water management for vehicle development? Well, about 50% of the time, vehicles are going to encounter some kind of adverse conditions while driving. So that's going to be snow, slush, wheel spray from other vehicles, rain, mud, dirt, dust. So all these contaminants from the environment can impact the performance of the vehicle. The ways that we can impact a vehicle with these contaminants is primarily through safety. So if you're going to lose visibility for the driver or for the computer system. Also, braking distance is impacted when you end up with water on your brake discs. There's also emissions, like, for example, brake dust emissions, which are starting to be tracked in Europe and other areas because they can cause cancer. Also, we also have issues with quality and reliability. So these would be things like customer satisfaction, so that when they go to open the door, they get their hand muddy because the soiling line has got up too high. Or if you're going to open your rear latch, and your hand gets dirty, or water runs off when you open the latch and drips into the trunk, for example. Also, people look at how often they feel they have to wash their vehicle in order for it to look clean. Then regarding reliability, there's issues with corrosion. So if you have water or salty water that's getting into the vehicle and depositing and pooling in certain areas, then that can cause issues with rust. There's also corrosion due to rock strikes. So if we have rocks hitting the underbody of the vehicle or certain panels, then those sites can be nucleation sites for rust as they get exposed to the elements. And finally, there's direct ingestion of the dirt, water, and snow into the engine or into the air intake system, which can cause issues. So a lot of our vehicle development programs now are looking towards autonomous vehicles, and with the goal being to have a level 5 autonomous vehicle. And for that really means that the driver doesn't have to intervene in any conditions, so that no matter whether or not there's snow, there's rain, the vehicle should still be able to handle that and continue to function. Otherwise, you're going to have drivers being stranded at the side of the road, which would be a very bad situation. So kind of no matter what we do, there's going to be dirt and water and debris getting onto the sensors. We're really just talking about trying to reduce the amount of that. So that means that for important systems, you're going to have some kind of cleaning system. And I'm going to throw a little bit about how we can use simulation to look at that. Also, I often get questions about coatings and whether or not coatings are the solution. They are part of the solution. They definitely help with removing the water and the oil if you get the right coatings. But what happens is over time those coatings degrade and they don't give you that same kind of performance. Also, with all these different kinds of coatings, there's kind of a residue that gets left behind, and that residue builds up over time and can affect. So you'll still need to have some kind of cleaning regimen or cleaning system for your sensors. Things that we're looking at doing when we're reducing the amount of cleaning that you have to do is reducing the size of things like your air compressor or your pump for your water, or even how big a reservoir you're going to have to maintain on the vehicle, because the smaller the reservoir, the less weight that you're going to be carrying around. There's also issues with wear, especially for wipers. So if you get a lot of dirt and grit deposited on, say, for example, the rear glass, then that's going to result in a shorter lifetime for your wiper blades. So currently, a lot of the regions of the vehicle that we really focus on are things like your door handles, so that's more for like getting in and out of the vehicle. Also looking at the air intake systems. Does dirt and water get directly into the air intake? And then we have the windscreen and side glass, which is mainly for driver visibility. We have most vehicles now have a rear camera, so we're going to worry about whether or not that's getting dirty. And then the rear latch and the license plate region, so you don't get a ticket for having an illegible driver's license. So with autonomous vehicles, the number of regions on the vehicle that we're going to have to maintain and keep clean is going to get much larger. So we're going to have all these sensors all over the vehicle for things like cross traffic, for collision detection, blind spot avoidance. So all these systems, when they get dirt or water on them, especially if they're cameras, are going to be impacted and their performance degraded. Even radar is impacted by water deposition. Especially the FMCW radar, which we're going to be using for detecting distance and velocity. So the distance at which it's going to be able to detect, or the strength of the signal coming back, is going to be impacted. So you can kind of see here, looking at this graph in the bottom right, that as we get water, we're losing a lot of the signal. But that's actually not the most critical factor, because we can compensate for that by increasing the amplification of the signal. The biggest problem is actually going to be with the looking at the change from electrical angle to physical angle. So when we're trying to detect which direction the signal is coming from, is going to be impacted by having this water on. So imagine that you have your sensor array and it only gets partially covered by water. So that's going to affect how the signal travels through that. And these chips that are associated with the radar systems have kind of baked in this mapping from physical to, or from electrical angle to physical angle. And that's accounting for the installation conditions, so that if you have different materials around, that's going to impact that signal and cause this kind of regions where you're going to have maybe multiple angles, so being returned as being the correct angle for which you're detecting. So you can kind of see here that ideally we're going to have this kind of one-to-one relationship between the electrical and physical angle, whereas once we start to get this kind of noise in the signal, it kind of becomes ambiguous as to which direction the signal is coming from. And what we do is we kind of correct for this for the install condition, but we can't correct for the water because we don't know where it's going to deposit and whether or not it's going to deposit uniformly over the sensor. So this is kind of a reason why we would like to keep sensors clean if possible. So what can we do with simulation design? With simulation design, we can look at the soiling line, so I can predict exactly how high up on the side of the vehicle the wheel spray for self-soiling is getting. So we can then suggest locations where you could place sensors. So for example here, if we put the sensor down in this region that are red, then it would be requiring constant cleaning. Whereas if we move up above the soiling line, it's going to be like once in a while, probably when you wash the vehicle, that you would have to clean the sensors. Real-world conditions also impact the soiling. So for example here, we have ideal conditions on the left which would be kind of like what you would see in a wind tunnel, very smooth airflow. But in reality, when you're driving on the road, you have the vehicle traffic, and that traffic creates turbulence, and these turbulent structures are going to impact the mixing of the soiling and water into the wake structures around the vehicle. So as you can see here on the right, that the soiling is getting up much higher on the vehicle. We're actually getting a lot of water deposited on the rear glass. So for example, if you design this vehicle in ideal conditions, you might think that you don't need a rear wiper, for example, whereas you might come to a different conclusion if you were looking at under real-world conditions. So you can see here clearly that that turbulence is helping to mix that water into the structures like the apellar vortex, and we're getting a lot more deposit on the side glass and much higher up on the vehicle. So with simulation, we can also look at different design changes and how that's going to impact the soiling. So for example, here we have a camera on the bottom of the mirror. So this would be looking for a blind spot. And what happens is with the original design, there was a lot of water and dirt getting onto that. So if you were driving behind, say, a bus, the kick up from that would be depositing onto the lens, and it would be impacting the visibility. What we did is we changed the mirror struts to change that vortex that's in behind that, and we also added some channels around the mirror housing, and that allowed us to drastically reduce the amount of soiling or dirty water that deposited on that camera lens. So if we're going to look at what does that mean for the camera view, you can see here that when you have this kind of film on the camera, you've completely occluded it, whereas with the better design, you're still going to have a fair bit of visibility for the camera system. The other thing that we get using simulation that we don't necessarily get from physical testing is the understanding of the mechanism that drives the soiling. So for that example that I showed with that mirror strut and and how that water is getting onto the camera, we did a simulation. Here we're tracking all these particles that are coming by, so these would be individual rain droplets, and looking at how they interact with the vehicle. You can kind of see that there's a mess, and there's a lot of stuff to look at, but it's hard to kind of pull out trends. What we can do is we can filter that data looking at a particular surface of the vehicle. So for example, here I pulled out the side glass and I said, okay, what particles are hitting this side glass? And then I can look at those traces and say, I want to see their entire time history for any particle that hit the side glass. And by doing that, I can see that most of the water that hit the side glass was coming from the bottom of that strut. So that means that I have to look at this region to improve the soiling performance. You can also use a volume. So sometimes what happens is you want to see like how much water passes through a particular region. So here you can kind of understand how that water is passing between the mirror and the sail of the vehicle. And then knowing that, you can kind of see how it gets impacted if you change the angle of the mirror or that spacing. We can also look at spraying systems. This is important for cleaning of your sensors. Also, we do windscreen sprayers. And what you can do is you can look at what the spray or how much of the surface is getting covered and whether or not you're hitting your target. How much of that spray is wasted. It's going into spraying other surfaces that you didn't really want to. And we can look at what the difference is between parked conditions and on-road conditions when you're driving at highway speeds. So for example, here we had this kind of camera on the front of the vehicle, and we had this little pop-out sprayer that pops out and sprays it. And it works really well if the vehicle's parked. But when the vehicle is driving, what was happening is a lot of that spray was going up over the hood of the vehicle and actually impacting the mirror. And if that's just doing that randomly whenever the system senses that there's dirt on the sensor, it could be kind of startling to the driver of the vehicle. We also have the ability to look at acceleration and deceleration. And sometimes this can be the worst case. So for example, you're driving along in your vehicle, you've got the water building up on the roof of the vehicle, on the hood, and all of a sudden you're going to slam on the brakes, and the simulation is going to do that in a second. And what you'll see is all that water rushes forward. And if we don't manage that properly and make sure that it gets channeled away from going onto your sensors or onto your front glass, then that would mean that you're obstructing the view as you're braking, which would not be a good thing. This also happens when the vehicle accelerates after being still overnight and you've had the rainwater kind of pool on the roof. If you start driving, that water will flow backwards and flow over your black windscreen. So this is something that we can look at. Okay, so using simulation, we can move the point at which you're able to look at this soiling and water management to much earlier in the design phase, because typically we're only able to look at this through experiment very late after we've got some test vehicles, because we have to do real-world like on-road testing or track testing to get this kind of information. But by moving it into simulation, we're able to do it at the same time as we're doing acoustic simulation or aerodynamics or thermal simulations. And that way we can make the proper trade-offs. So we understand that if we change a certain corner on the vehicle, that the soiling line is going to move, but that means that we need to have more sprayers, and then that would maybe mean that you have more weight to carry around for spray. And that might not be a good trade-off. Or, for example, you could change your braking system to improve your cooling, so introducing more airflow onto your brake, but you might also be putting more water onto it and reducing your braking efficiency. All right, so now I'm just going to go through a few case studies. So the first case study here is just looking at a rear camera mirror. So in this vehicle, what we were looking at is we were looking to actually reduce the ride height to improve aero efficiency. So by dropping the ride height, we were getting a significant change in the drag of the vehicle. Unfortunately, it also meant that the amount of soiling on the back of the vehicle increased significantly. So that meant that we were 3 times more likely to have water hitting the camera of the vehicle. So then that's all right, but it's good that we knew that that was going to happen. And then we would know that like this is also probably going to mean that we're going to need a rear wiper. And then we could look at the trade-off between the wiper system and the cost associated with that versus the reduction in the fuel economy. Again, using those particle traces that I was talking about earlier, we can look at how the water is getting from the wheels to the rear face. And you can see here that a lot of that water is coming from those rear tires and it's kind of being pulled inwards towards the center. And that gives us ideas about how we could impact that. So for example, by putting like rear mud flaps or by changing the bumper here, the rear bumper, we might be able to get better separation between the rear wheel wake and the base wake. We can also look at water ingestion. So for example, if we have a vehicle, this one here is a truck. A lot of the times for trucks, the air intakes are on the sides, especially for North American trucks. We can also do European trucks where it's kind of more up into the back. And what we can look at is under driving conditions or emulating SAE standard tests, how much water is getting ingested by that vehicle. So here you can see that this one has fairly poor performance with a lot of the water getting ingested into that air intake there at the center. And what we would do is we would work with the engineers for that vehicle to add baffles and to drain that water away. At the same time, we'd be balancing that with the pressure drop that gets introduced by adding those baffles and turns, and ensuring that we get the optimum design. I talked about during the introduction about brake dust and how that's becoming a significant metric for the industry. So here we can see the brake dust and how we simulate that with it passing through the wheel. So this is important for warranty issues. You can have these brake dust deposited on your paint and cut and sinter, and that can become a nucleation site for rust. Actually, I had a customer where that happened, and they actually had to have a recall and actually buy back a few vehicles because of this. And all of it stemmed from a change that they did to a brake dust shield. And then once they reinstalled that brake dust shield, the problem went away. So you can see kind of here what we're doing is we're emitting the particles from the contact patch of the brake, and then we're able to track them through. You can also do things like looking at vacuuming systems for trying to collect that dust and make sure that it doesn't get released into the surroundings. You can also rank different wheel designs. So you could have different hubs and spokes and looking at which ones will give you better performance as regarding cleaning. So again, this is really difficult to clean off the vehicle, and it requires scrubbing. So customers sometimes will complain about that. I also mentioned brake wetting and how the brakes getting wet will impact the braking distance. So here's an example where we were looking to improve the cooling of the brake system by adding an air duct. And we were ducting that air to the brake, and then what it was happening is some of the water that you would have coming from the traffic would be coming through the through that duct along with the air, and then it was being directed onto the brake. And so you can see here kind of those blue spots, and those blue spots represent droplets of water that we're hitting. So you can see how after a period of driving that you would get a significant amount of water build up onto the brake itself. And we could rank different designs looking at how you do different bends in that brake duct, and then you can end up separating a lot of the water out and reducing the amount, or making it so that you have more dry air impacting onto the brake. All right, so we feel here that we have a industry-leading solution for tracking particles and water film on the surface of the vehicle, and this can help us to improve the safety of vehicles by keeping sensors clean, improving driver visibility, as well as keeping brakes drier and managing brake dust. We can also help with the quality of the vehicle by, again, moving those soiling line down, keeping the driver door handles or the clean and free from dirt, is also making the rear latch not get dirty. As well, we can improve things like the life of your filters by reducing the amount of dust that we're ingesting into your cabin air or into your air intake system. And we can help you to make the making decisions about trade-offs. So whether or not changes that you're going to do, for example, to your aerodynamics of your vehicle are then going to result in complaints from customers related to soiling or water management.